Now postulate number 3. So first postulate we discussed about the wave function, and in the second postulate we said about the observables are associated with the operators. So what is the outcome of these two? The outcome will be the value, which see in the lab we are going to measure, we will get some values. So these values are nothing but eigenvalues. Okay, so this is eigenvalue equation, and A operator operates on wave function will give you eigenvalue with a wave function, and this must be a real value. So lambda must be real. So operator operates on any function will give you eigenvalue with a function. So we know already this eigenvalue equation earlier, and this will give you eigenvalue. So eigenvalue equation. Okay. So given operator may have several different. For example, this eigenvalue equation can be written as exactly like this. Okay. Suppose if we have number of particles, system consists of number of particles, number of linear combination of wave functions. Then we can write, instead of a psi, can write a psi n equals lambda n psi n. For several wave functions, we will have several eigenvalues. Several wave functions will have several eigenvalues. Okay. Suppose in classically, okay, I am going to measure this one. So it can be around 10 to 15 centimeters. So it can be say 15 centimeter. And if I ask any one of you to measure this one, it will be also 15 centimeter. Correct? Suppose if I measure tomorrow, that will also be 15 centimeter. So this is deterministic value. Suppose if I am going to measure a quantum system today, now, okay, after some time I ask any one of you to measure the quantum system. It can be the same or it cannot be the same. It need not be the same. Very, very important concept in quantum mechanics. If I am measuring the same point tomorrow, it need not be the same. We will have different values. It is not guaranteed that we will have a same value. No, we will never have a same value. Sometimes we will also have same value, but we can't expect that we will have a same value. So each measurement we may get a different eigenvalues. For different wave function we will have different eigenvalues. It is not guaranteed that we should get the same value. So we can't get the same value, then we will have to go only with the expectation value, average values. We will not get the same value, correct? So only then we can go for the expectation value, average value. So that's why eigenvalues are always closely related with the average values. So eigenvalues are expectation values, which we are going to see. So experimentally what we will do? So number of measurements, we are going to measure number of measurements. For example, if we are going to measure n1 times, we will get the eigenvalue lambda 1. And you are going to measure n2 times, number of times, and you are going to obtain lambda 2, eigenvalue lambda 2. And measurement n3, that will obtain n lambda 3. Okay, then we are going to take the average value. So when you are going to take the average value, the formula is nothing but n1 times lambda 1 plus n2 times lambda 2 plus n3 times lambda 3 divided by total number of terms that we are going to measure. So this is experimentally we can do. We are doing experimentally the same method. Quantum mechanically, what we can do is we will take the expectation value. That is, operator operates on any wave function, and multiply it by its complex conjugate will give you the expectation value. Okay, if it is not normalized, then we will have to divide by the normalization constant. Okay, if it is normalized, the answer will be 1. So you will have expectation value is nothing but only the numerator alone. If it is not normalized, you will have to divide by the normalization constant like this. So this experimentally observed values, this is quantum mechanically theoretical values, both are the same. Okay, if the state function is eigenfunction, for example, if the state function is eigenfunction, then we can say that suppose both functions are the same, what we call this as eigenfunction. If the state function is eigenfunction, then we can say that A operator on psi will give you small a times eigenvalue with the operator, correct? A psi equals small a psi. A is a value, I can pull it out. So I can write A psi star psi d tau divided by integration psi star psi d tau, both will get cancelled, you will have A. Expectation value is nothing but the eigenvalue, provided the state function must be eigenfunction. The state function must be eigenfunction. Is it clear? I repeat. See, the state function is eigenfunction. Both the wave functions are the same. We have a state function, and this function also it's the same. It's an eigenfunction. If it is so, then A operator operates on the function will give you A psi. You pull A out, both numerator and denominator are equal, so both get cancelled. You will have only value A. It says that the expectation value of the operator, which is nothing but A itself, provided the wave function is eigenfunction. So that's very important conclusion. If you take large number of measurements, the average value is A. In the special case, when the state function is the eigenfunction of A. For example, we will have just take a linear harmonic oscillator. So we discussed just now linear harmonic oscillator. We are going to discuss linear harmonic oscillator in detail in the next unit. Okay, linear harmonic oscillator. We have operator method, as well we have ordinary wave function method. Okay, so linear harmonic oscillator, in which we have a Hamiltonian operator, which is nothing but sum of kinetic energy and potential energy. This potential energy is nothing but half kx squared, where k is the force constant. So we will have to use eigenvalue equation, and we will get the result as the value eigenvalue is nothing but En equals n plus half h bar omega, where n goes from 0, 1, 2, 1, 2, 3 goes on. So we will discuss later, no worries. Suppose we are going to measure the Hamiltonian operator, with a wave function. We will get any one of the eigenvalues, correct? Any one of the eigenvalues, it can be h bar omega by 2 or 3 h bar omega by 2 or 5 h bar omega by 2. Any values will get, correct? Any one of the values. Use the Hamiltonian operator, operates on the wave function, will give you eigenvalues, any one of the eigenvalues, correct? Am I correct? Suppose if we use the wave function, which is the same psi, it's nothing but psi star, it's the same wave function, what we call this as eigenfunction, then it is sure to get only the particular eigenfunction. If you measure number of times, for example, you just take n equals 2 here, n equals 2. When n equals 2, you will get only 5 by 2 h bar omega, correct? When n equals 2, you will get 5 by 2 h bar omega. If you measure n equal to 2, number of times you will get the same value, correct? Earlier I said, if you take, if you measure the different value, you will get different wave function, you will get different eigenvalue. Even with the same function, after some time also if you measure, you will get different eigenvalue, as I said. But now I am saying that if you take n equals to number of times, if you measure, you will get the same eigenvalue, correct? 5 by 2 h bar omega. So earlier we said it is not guaranteed. It is not guaranteed that we should get the same value. But here I am specifying, saying that for n equal to 2, if you get number of times, if you do number of times, you will get only 5 by 2 h bar omega. So this is just a contradiction. Okay, this is called decoherence and measurement theory. Still research is going on, okay, on this. So if the wave function psi is normalized, then the expectation value is given by this. The expectation value of the potential energy can be expressed in equation 1.140. Now we will go for the last postulate number 4. The time development of quantum system. So h psi equal to E psi. So that is the last postulate. So we know that psi depends on both position and time. Okay, position coordinate. T stands for time coordinate. Okay, how the wave function evolves with time. So at 10:45, my quantum system is here. At 11 o'clock, quantum system may be somewhere. How it changes with time, how it evolves with time. So this is about the time development of quantum system. Okay, so the time development of quantum system can be studied with the help of equation of motion. So we are going to do. It is a differential equation of physical variables which describe the system, and it is given by, of course we know h psi equal to E psi, and instead of E you can write the operator form. So I h cross d psi by dt equal to h psi. Correct? So now wave function is a differentiation with respect to t. Okay, how it evolves with time. So d psi by dt says that the wave function changes in time. So how we are going to find out? The wave function itself will be the answer, which is equal to h psi. So which depends on Hamiltonian operator h, which is nothing but sum of kinetic energy and potential energy. So the evaluation of operator d psi by dt is related with h, Hamiltonian. H is nothing but sum of kinetic energy and potential energy. So psi of r is the eigen function of the Hamiltonian operator corresponding to the eigen value. So this h is, just now I said, is a sum of kinetic energy and potential energy. And of course here psi depends both x comma t. So we have to use time dependent Schrödinger equation for the time evaluation operator. Okay, we have to use time dependent Schrödinger equation to find out the time evaluation operator. Is it clear? Okay, so we can solve this equation and get psi of x comma t. So the equation says how the wave function evolves with time. The Hamiltonian operator determines how the wave function changes with time. So the time evaluation of the quantum system is governed by Hamiltonian operator. Hence the Hamiltonian operator is very important in quantum mechanics. Okay, what are the consequences? So we are going to look into, in 2 slides, we are going to look into the consequence of these postulates. The one is the expectation value. Okay, so we know the expression for expectation value is given by this. A is sandwiched between your normal wave function, ordinary wave function, and the complex conjugate. Suppose if the wave function is eigen function, then we can write A operator operates on psi, that will give you this equation, and we will have A. So expectation value is nothing but your A value. So A value is a sharp value. It's a sharp value. Correct? Your expectation value is nothing but ordinary A. If it is, the wave function is eigen function of the wave. So if the system exists in a state such that the observable exhibits a sharp value, then the state is called an eigen state of an observable. So continuation of that one will give you, suppose any system psi can be expanded in terms of expansion theorem. We know already this. Correct? Sigma over I Ci psi I. So capital psi equals Ci, summation over I Ci psi I, we know already. We will go with the complex conjugate. Then psi star will be sigma over j Cj star psi j star. The expectation value can be calculated using this expression. Correct? Okay. So operator A acts on psi multiplied by its complex conjugate, that will give you this. Now you substitute. Psi star is given by this expression, psi is expressed in this expression. You substitute these two expressions in this expression, you will get this. Correct? Come on, psi star will be sigma over j. So sigma over j, Cj star, and A is here. Your psi will be sigma over I Ci star. So I written Ci psi I d tau. Okay. A operator on psi I will give you Ai psi I. I can pull Ai out. If I equals j, Kronecker delta function, if I equals j, I can get this as equal to 1. I can get as 1. So you will have the expectation value is nothing but the square of the amplitude multiplied by the eigen value, any one of the eigen values, Ai or Aj. So eigen value. Correct? So we know already psi equals sigma I Ci psi I. Okay. I am going to multiply on both sides by psi I star. I am going to multiply on both sides by psi I star. So psi I star psi, which is equal to Ci psi I star psi I. Is it okay? Psi I star psi I will be 1. So sigma over I Ci, that will give me Ci. So Ci can be written as integration psi I star capital psi d tau. So the amplitude is the coefficient. This is nothing but probability amplitude. So C is nothing but constant. Okay, that Ca squared. You just square it and you can write this. Okay. So this is nothing but the inner product, finding the particle, finding the system in the final state once you make the measurement on the initial state. Okay. So this will be your initial state and that will be your final state. So this is nothing but eigenvalue multiplied by the inner product. This is your inner product, square of the inner product. So when this is also one of the consequences. So when the system is in the eigenstate psi I, the probability occurs at the value ai in the measurement a. The expectation value a is a sum over all possible eigenvalues with a probability density. So this is the probability density. Okay, that's nothing but square of the inner product. Okay, this is nothing probability density. So this is one consequence. The another very important consequence is the stationary states. So suppose we know that, of course we know that electrons will not have orbits. Suppose if we consider electron goes with the orbit, okay, in a circular manner, then this will have only stationary states, standing waves. So just now we discussed the fourth postulate, which says that we'll have to use only, this is the evaluation of time operator, correct? Evaluation of the operator. We'll have to use only time dependent Schrödinger equation. We'll have to use time dependent Schrödinger equation. The potential energy also depends on both position and time, correct? In special cases where the potential energy does not depend on time, in special cases, then we call this as a stationary state. We say that this is a stationary state. If potential energy does not depend on T. If potential energy does not depend on T, then we already studied, we discussed in this link in YouTube that using separation of variables, we have divided time part and position part. We have already studied. So we will have to use that technique to separate the wave function into time part and position part. We have already studied. Okay, so we are going to use that idea. Now we just look at this one at t equal to 0. Okay, at initial state. So this is my wave function. We consider this as a wave function. As time changes, as I said just now, 11.5 one wave function is there. Then 11.10 the wave function may change with respect to time. So wave function may change with respect to time like this. So at t equal to 0, that is at t naught, the wave function may at t equal to t something like this. Suppose if there is no change, it is a special case in which potential energy does not depend on t. Then we will have to use the separation of variables, and this is the technique of separation of variables which you have already studied in this YouTube link, and we have obtained psi n of r comma t equals psi n of r e power minus I e n by h bar t. You just square this one, take the complex conjugate, you will have e power minus I e n by h bar into t multiplied by, take the complex conjugate. So it will be e power plus I e n by h bar t. Both will cancel, you will get 1. Correct? So you will get psi n of r. So in one dimension we can write psi n of x mod psi n of x squared multiplied by the probability square of the probability. Correct? System consists of position and time. System depends on position and time. Left hand side. Right hand side there is no time at all. Left hand side we have time. Time is there. System evolves with time. And right hand side there is no, it does not depend on t. It means it refers a stationary state. Stationary states is nothing but there is no transition between two states. There will be no transitions at all. So this is called the stationary states. This is something like standing waves. So in stationary states, all the atoms will have standing waves. So this is integral multiple of lambda. That is the idea. N lambda. It will be in terms of n lambda. That was a prediction by Niels Bohr, and it was put forth by de Broglie. So this is de Broglie's concept. Stationary states. Okay, standing waves. So at standing waves, we will have no transition. So stationary states, there will be no transition at all. So all the electrons will be in the stationary states. So that was the prediction, and it was the idea of Niels Bohr. Okay, the probability does not change even though system is changing with time. Okay, with the time, and the probability amplitude remains the same. This probability amplitude will remain the same at all time. So this is called the stationary solution of Schrödinger wave equation. So that is the end of the class. Okay, we will close it. We have already seen the enough concepts of postulates of quantum mechanics. We will see in the next class.